and I'm also the director of medical physics. We have an accredited program in medical physics. And I teach normally radiation transport, radiation interactions, Monte Carlo methods, and radiation biology. And the treatment planning is such a very broad area. I try to appeal to everybody who has an interest in it. But if you lack something, if you miss something, just stop me and ask me. So let me give you first an overview. I will talk about basic dosimetry concepts first, and in that charge-particle equilibrium is very important, and then we are going to progress to depth dose, output factor, and isodose curves. And then we'll look at dose calculation methods, and there is the traditional dose calculation methods that we are going to look at, conventional, and then the most modern ones, which are based on convolutional superposition techniques and also Monte Carlo. And finally, we'll go into 3D treatment planning, and we'll go through the elements of those, including the delivery methods, immobilization, target volume definitions, beam arrangements. And finally, we'll look at the use and how to put together, and then the use of those volume histograms and their role in the treatment planning. So first of all, we had to talk about what is treatment planning. And broadly defined, it is the process of determining the most appropriate way to treat the patient. And this includes several elements. First, we have to identify the treated volume, the shape, location, and the neighboring tissue, including the organs at risk, those organs that are vulnerable to radiation, and we cannot afford overdosing them. Important aspects are reproducibility, patient positioning, patient and immobilization. So immobilization is important through the fraction, and then reproducibility is important between fractions. Beam arrangements, we will spend some time on that a little bit later, so this is one of the processes. And of course, evaluation of the resulting dose distribution is extremely important. And finally, this goes into calculating the treatment machine parameters to deliver the prescribed dose. So all this requires a pretty good understanding of radiation physics, radiation interactions and transport, machine characteristics, and dosimetry methods. So let's start with some of the basic concepts. And one of the very important concepts in radiation therapy is charge-particle equilibrium. Charged particles in photon therapy and in electron therapy mostly means electrons. So let's assume that we have a uniformly radiated volume, as you see here in this cloud. Let's assume that this is uniformly radiated by an external beam. And in the case of charged particle equilibrium, every particle track that starts at a volume element, there is a similar one starting in an adjacent element. So I subdivided this cloud into equal volume elements, and you see the starting and ending positions of a charged particle track. A, B, C are fragments or fractions of a charged particle track originating in one voxel or one volume element, going through another, and then ending up the white one in the center is. Is there a question? No. Okay. So the white one is the volume element in which we are interested in the dose. So as you see, there are contributions to the dose by charged particles coming from adjacent elements. And in equilibrium, what happens is that each charged particle of a given type, like electron in this case, and the energy leaving the volume, which is the white volume here, is replaced by an identical particle entering the volume. So under this, we call it charged particle equilibrium. And as a consequence, we can calculate the dose much easier easier than in case of disequilibrium. Charge disequilibrium, which is the lack of equilibrium, occurs at or near particle sources and at interfaces of disparate materials. So, for example, here is a little cartoon when there's air and then tissue, and X-rays are incident on the tissue. And because X-rays sparsely interact with air, there is no other charged particles, not really many, that would enter tissue from air. So most of the charged particle generation by radiation interactions of X-rays, interactions by, for example, photoelectric effect, or interaction by Compton scatter, will start really in tissue. And as we subdivide the tissue to layers, there will be initially very few of these electrons that are generated, and then as we go deeper and deeper, and as radiation goes deeper and deeper into the tissue, there will be more and more of these charged particles generated. So one way to look at it, just simply in this arbitrary case that is drawn here, just look at the number of charged particles produced by these downward pointing arrows in these various layers. So layer 1 has just one charged particle produced, which is one arrow ending in layer 1. And on the right-hand side, you see the dose in layers. So this is entirely arbitrary. This is just for illustration purposes. So in layer 1, we have a dose of whatever 1, or particle 1. In layer 2, we are going to have 2, and 3, and 4, etc. And it goes up, and more of charged particles are produced, and eventually it starts to peak at about layer 5. And from there on, we start to see attenuation, because not all of the X-rays will reach the depth. And as fewer and fewer X-rays reach this depth, there's going to be fewer and fewer new particles produced. So whereas in layers 1 to 5, we had newer and newer particles produced, charged particles produced, later this becomes kind of in a transient equilibrium. There's no more new particles because the incident X-rays start to attenuate. So we can actually plot this, and on this, on the horizontal axis is the depth in tissue, on the vertical axis is the dose, and the black line, the solid black line, indicates the absorbed dose, and as it goes up first, it eventually reaches the maximum, and then it starts to go down, which is known as the region of transient equilibrium. And the build-up region is the region between the at the surface where the particles are incident up to the maximum value of the dose that it reaches, and we will call it the Dmax, the small d max. Small d is the depth, and the subscript max indicates the depth at which the dose peaks. So in charged particle equilibrium, computationally, we have a lot more reduced complexity, because in this case, it's like a point function. The kinetic energy released in matter can be used, the kerma can be used to approximate the dose. Kerma is an abbreviation of kinetic energy released in matter. And in this case, what we do is that all transferred energy by an incident particle is assigned to that spatial point where the particle first interacted. In other words, we are not following all the secondary, we are not looking at what happens beyond the first interaction site. At that interaction site, we are going to say that the energy that was transferred there will stay there. But this is markedly different from the dose, because energy transferred to material means that maybe we have a secondary particle, like an electron. And that electron that has now a kinetic energy may actually fly out of this region and takes remaining energy with it. So this is very difficult to calculate. The dose is difficult to calculate, but the kerma is relatively easy to calculate because it's a point function. So at that point of interaction, we calculate the energy transfer, which is on the right-hand side. You can see this, that in CPE, right to this chart, the CPE is which is in charge particle equilibrium. can be approximated by Kerma, and which means that we can just use the mass energy absorption coefficient, mu-En, times the fluence, the particle fluence, the incident fluence there at that point in space where we want to calculate it, times the energy of the particles, which is phi times E. Phi times E is also known together as the energy fluence. So this is a much easier way to calculate things. The depth dose, of course, changes, and this is a way to calculate the depth dose. So on the right-hand side, in the upper right quadrant, there is a little cartoon showing you the X-ray source and how the X-rays might be incident on a phantom. And through the collimators, and it shows some definitions: source to surface distance, there's SSD, and then there's a central axis, and the percent depth dose, PDD, is defined as the dose at any point along the central axis, along the depth of the phantom, divided by the dose at a reference point along the central axis, which is D sub 0, and then this ratio multiplied by 100. So that gives you a percentage. So the depth dose at the reference point is most often, the reference point is defined the Dmax. So the depth at which the maximum dose occurs. On the left-hand side, there are two charts. One is the photon beam central axis depth dose, and the other one is below is the electron beam central axis depth dose. And as you can see, depending on the energy of the incident photons and the incident electrons, the depth dose variation significantly changes, and the location where the maximum of the dose occurs, which is the Dmax, also significantly changes. Obviously, the higher the energy of the incident particle, the more material is needed, the more travel in the material is needed to form the maximum dose. So the dose buildup is going to be a thicker amount of material. So what happens is that as you see in for the photon case, is that for MV beams, you will see a protracted Dmax, whereas for KV beams, for example, the 3 mm copper half-fiber layer filtered X-ray, there's almost region, it looks like. So this means that the Dmax occurs kind of in the skin. So if you increase the beam energy, that has a skin sparing effect, because the dose will be much lower in the skin. And the same thing happens, or similar thing happens with electrons. On the right-hand side, on the lower right quadrant, you see the field size dependence. So it not only depends, the depth dose not only depends on the beam energy, or the beam quality sometimes we call, but it also depends on the beam size. So the lateral size of the beam, how large it is. So as you can see, that if there is a small field like this, like curve C here on the lower right quadrant, half a centimeter by half a centimeter field, the Dmax is going to be a lot smaller. Maximum dose is going to be a lot smaller than in case of B or A, which are increasingly larger field sizes. And of course, as you can see and also read, the slope of fall-off is also different with increasing depth as function of field size. The effect of heterogeneities is extremely important, because we have a loss and restoration of charge particle equilibrium, and this can cause a clinical problem if we don't take care of that. And this is obviously commonly occurring near heterogeneities, and such heterogeneities would be an air pocket, for example, because or a lung, of course, is another structure. And the structure where this happens, and also there is a change, a transition of disparate materials. We will see this. And of course, dose buildup is due to the building up of the population of the electrons. So in the present case, as you can see here, it is an air cavity. So the beam is incident on the left on the skin, and there is tissue, and then there is an air cavity somewhere in the tissue. And the dose goes up as we discussed, as the dose builds up and reaches a maximum at Dmax. And then as the particles reach the air pocket, there will be fewer secondary particles, fewer electrons generated in the air by photon interactions, yet the air, because electrons are densely ionizing radiation, air can still absorb these electrons. So there is absorption of electrons in air, but there's no replenishment of electrons in air because photons are sparsely ionizing the air molecules. So as a consequence, these are removed, and they will be smaller and smaller contribution to the dose. That's why you see a drop-off in the dose. The thin line represents the dose drop-off without the air cavity, and the thick line represents the dose drop-off with the presence of the air cavity. And then there is a dose build back up, a build up. So there's a build down, and then there's a build up, because now as the particle starts to reach the other end, the other side, the distal side of the air cavity, there will be more and more electrons coming back from photon interactions on the far side of tissue. So now suddenly we start to see a build-up very similar to what we saw a skin sparing effect, a skin build-up here at the beginning. So this is like regain, as we call it, regaining skin sparing. There's no skin, obviously, but sometimes people refer to as regaining a skin sparing effect. So as we have another build-up here. So this is very important to know, because unless you take care of this problem, the patient will be undosed or overdosed in different structures. There are several very important dosimetric parameters that we are going to use later in this lecture. So let's go through this a little bit. So one of them is the tissue-air ratio. And this is a very simple concept. Look at this cartoon here. There are two parts of it. On the left-hand side, there's a phantom. And on the right-hand side, it's equal conditions. Everything is equal except I take the phantom out. So the TAR, the TAR, or the tissue-air ratio, is the ratio of the absorbed dose at a given point in the phantom, at some kind of depth, called D, in the phantom. And we divide this with the dose, the absorbed dose, at the same place, but when we remove the phantom, so that is, in other words, we call it a free space. That would be measured exactly at the same point, but there's no phantom there. So obviously, it's not an easy thing to measure this in free space. We put a very small phantom, we call it a mini phantom, to generate an equilibrium mass there. And what is interesting here is that the TAR is a function of depth, obviously, because as you go farther from the source and go deeper into the phantom, the dose will be different. But because it's a ratio, it's not really a function of the source distance, because both of them will be the same distance, the same inverse R square law, the dose drop off. So as a consequence, it will not be dependent on the source distance. So this is a tissue-air ratio, is something that will come back many times to see. Tissue phantom ratio and tissue maximum ratios are also defined very often. So TPR, which is tissue phantom ratio, and TMR, tissue maximum ratio, are used as alternatives to the TAR for high energy radiation, because in free space, again, in air, it's very high energy photons are sparsely ionizing. So it's very difficult to measure high energy photon dose in air because of this, and there's a lot of uncertainty with it. So as an alternative, we often use the tissue phantom ratio, which is the dose as ratios at a reference depth d at dr, and which is directly measurable over the entire range of the X-ray energies. And so this is the dose at some depth divided by the dose at some reference depth, and then it is multiplied by 100. So if this reference depth happens to be the Dmax, then TPR will be something like a PDD. The tissue maximum ratio is analogous to this, except the reference depth is now Tmax. So this is the PDD essentially, but there are subtle differences depending on how we apply this. Because, and here's the subtle difference, is not quite the PDD because this Dmax greatly varies with beam energy and with source surface distance and field size. So instead of one Dmax, what we use is a Dmax which is equal or greater than the largest Dmax. So that's why we call it the maximum ratio, the tissue maximum ratio. Further two quantities that are important are the scatter error and scatter maximum ratios. So these are, the scatter error, SAR, is essentially the scatter component of TAR, which is simply the difference between the TAR of finite field size and zero field size. And of course, many times the question is, how can you measure the zero field size? Well, obviously, it's an approximation. It's an asymptotic chamber. You're using an asymptotic chamber where you gradually change the volume to next to zero. And this way will be a good approximation of zero field size. The scatter maximum ratio is very similar to this one, except the TAR is now multiplied by a correction factor. And this correction factor accounts for the changes in the scatter radiation originating in the phantom at the reference depth. And this SPR is the phantom scatter correction factor, and then it's just a ratio with finite field size divided by the same with zero field size. Otherwise, so this is the TMR at D with field size E and energy E is multiplied by this correction factor in the scattered ratio, and that becomes the scatter maximum rate. I'm sorry, this was very difficult to understand. Can you say it again, please?
Hello, we're trying to hear you. Okay.
I don't hear it.
Yeah, just continue, please. Yeah. Just continue. I think she will.
Just continue. All right. Let me know, please.
Yeah. You can.
Okay.
Just, yeah.
Or maybe you can email me.
Yeah.
Questions.
Yeah. Sure. All right.
Okay.
Just, yeah.
All right.
Thank you.
Okay. Very good. So some other important concepts is the output factor and the ratio of the dose rate at Dmax for a defined field size to that of a reference field size, which is a reference field size is usually 10 by 10 centimeters, which is also measured at the Dmax. So this is the output factor. So the output factor has two components. One is the collimator scatter factor, which is R is the size of the collimator opening projected at the isocenter, times the phantom scatter factor, which is a function of the effective field size, which is R. R is the effective field size, which is irradiated at the treatment distance. So this is on this figure. You can see the field size dependence of the output factor. So on the horizontal axis is the lower collimator setting, and the parameter as starting with the lowest curve 4 and then 5, 6, 7, 8, 6, 8, 10, 15, etc. These are the upper collimator settings. And on the vertical axis, you see the relative output factors. And so as you see with the parameter of the upper collimator setting, eventually as you increase the lower collimator setting, the output factor starts to taper off. So in other words, with increasing field size, you start to taper off. Now, if you have square field, which is the dashed line with bullets, is indicative of a square field. So if you have square field, then it doesn't really taper off that rapidly, but still there is a tapering off tendency as the field size increases. The relative output factor increase is not as dominant. So we often want to represent the dose in terms of isodose curves, and isodose curves represents points of equal dose. And we connect the points of equal dose, and then when you do that, usually we give it in 10% increments, normalized to the dose at Dmax. So this is all again a percentage in terms of Dmax, and it's most often, at least at experimental treatment planning, we do it in the 2D dose profile. Nowadays we do 3D treatment planning, and 3D planning we have these dose surfaces or dose clouds, but still we are using the two-dimensional ones because CT slices are just two-dimensional slices, and we often just overlay the two-dimensional isodose curves on the CT slide. And on the left-hand side, you see, for example, a cobalt-60 beam with a source-to-surface distance of 80 centimeters, and then a 4 MV beam, 10 MV beam. And as you see, as the energy of the incident beam increases, the dead dose curves, the isodose curves, the 100% isodose, which is the Dmax will be deeper and deeper. So as we see, for cobalt, it's almost at the surface. At 4 MV is a little bit deeper, and then 10 MV is much deeper. So consequently, also the various types of those curves, 90%, 80%, etc., will go deeper and deeper. And if we wedge it, in other words, we put some compensator in it, for example, like a wedge, then it will be skewed. So wherever, and it shows the wedge is thicker on the left-hand side and thinner on the right-hand side. So where the left-hand side obviously it degrades both the number of incident photons as well as the photon energy will be different, right? So in MV cases, which is not shown here, MV case actually there is a beam hardening, whereas a cobalt case, which is a monoenergetic, two photons, one is 1.17, the other one is 1.33 MeVs. So because these are monoenergetic lines, there is no beam hardening, but there is attenuation. So that's such a huge attenuation, as you see here. Oftentimes, we also plot the beam profiles at the depth of the maximum dose. So here is one at the depth of Dmax, and then there is one at 10 centimeters. So what you can see here is what's interesting is that the off-axis distance dependence. And if you are close to the central axis, like the innermost curve, there's not much difference in the way that the dose profile looks along the central axis, close to the central axis. So when you compare the Dmax, the location at the Dmax versus 10 centimeters, there's barely any difference. However, as you go out in the off-axis, farther out from the central axis, this is in the beam profile. So look at the 40 by 40. A beam profile going out there, there's a fair amount of difference in the dose curve, the location of the dose curve. So a big question is that how do we calculate these doses? And not only how do we calculate, how do we measure? Because it's a combination of things. In the very, very old days when I started my career, we measured the doses in phantoms, and we also could do some computations. And the computations were made, and still, you can see these quite often that we do hand computations and maybe computer computations, but not very sophisticated in terms of Monte Carlo, but more like more like the CPE type of equilibrium calculations. So assuming charge particle equilibrium, we can use the formula that I showed you earlier, that dose equals the mu En over rho times the energy fluence. Or we can actually measure it in a water phantom. And because this calculation doesn't take into consideration heterogeneities, doesn't take into consideration sloping skin surfaces, that skin surface is not flat like a phantom is, and there are heterogeneities in a human, and of course then beam modifiers, etc. We have to correct these doses based on what is the problem at hand. So this is one type of dose determination method. It has been around for a long time. It still is around in some cases, but most modern treatment planning now uses convolution superposition methods, like we call kernel-based models, and you'll see why we call them kernel-based models. So these are, rather than measuring it and using the measurements and adjusting the measurements, these are pure computations. But of course, the computations are also based on measurements. We have to. It looks like there may be some questions.
No. I think there's just a background noise, but that's okay.
The background. Okay.
Yeah.
Okay. Very good. So obviously, even
Just give me a break. All right. Can everyone please mute their computer, please? I'm trying to get where the noise is coming from. Oh, I've seen it. Don't worry. Just go on. All right. You can go on, sir.
Okay, very good. Thank you.
Yeah.
So even with the most sophisticated computer models, we need to have some measurements because we have to verify things. So when I say pure computation, the pure computation is only after we have verified that the computation. So we actually put into the treatment planning computer a database, which is the output factors and various other machine-based parameters, which now use the computations we use, and of course we have to verify this before we execute it on patients. So, but let's go into the details. So this is a conventional dose correction method based on conventional calculations and measurements. So this is not something we do for kernel-based or Monte Carlo-based techniques. So, but it's very important to know about them because it keeps coming back. So one correction method is for sloping skin surface under the beam. So this is known as the ratio of tissue air ratio, or the ratio of tissue phantom ratio. And one technique in this is that, as you see on the left-hand side, there is a cartoon with a sloping skin surface. And these isodose curves are based on either measurements or simplified calculations based on a phantom. And we select a point in the tissue, like in A here, above which the skin surface is almost flat. So may be considered unaltered compared to a flat phantom case. Consequently, the dose distribution at point A at this point is also unchanged compared to the non-sloping phantom case. But at a different position, there could be a substantial slope of the skin. So at both the primary and scattered dose components are substantially different from a phantom case, and we have to make a correction factor. And the correction factor is simply a ratio of either the tissue air ratio or the tissue phantom ratio. So either which one will actually work. And here the tissue air ratio, tissue phantom ratio is evaluated at d minus h, where d is the distance of the dose point in point B from the flat surface case, and h is the distance of the skin from the flat surface case, which is like an air gap, and d minus h represents the tissue depth at the dose point B. And SD is, of course, the beam dimension or field size at the dose point. And then this is divided by the tissue air ratio at the depth, at the depth of the tissue from the flat line. And the correction is then executed by taking this correction factor and multiplying the idealized dose distribution, which is represented by these isodose curves. So another method is a similar one, but yet another method of correction factor is that the isodose charge is placed on the patient contour, and it is shifted down along the beam direction by the size of the air gap, by the size of this H, and this is the dashed line. So this is so the PDD value at point B is read and modified by the inverse square law to account for the effective change in the Dmax. So in this case, the correction factor can be defined away, but now we are using the ratio PDDs. So PDD is a D minus H, which is the same D minus H as before, at Dmax, with the field size and with source surface distance and energy. So these are all dependent factors. And then we multiply this by the ratio of source surface distance plus Dmax divided by the source surface distance plus Dmax plus this air gap H squared. And this is just another technique of doing it, and it's arguable which one is better than the other one. Then there's yet another one, which is the isodose shift method, which is a simplified correction. So even though we say that, well, the effective source skin ratio, which is this, or the random ratio, are not really very accurate, it's very difficult to execute them. If you have to do it by hand, it's very difficult to execute them manually for every dose point. So there's a simplified correction method in which we look at diverging X-rays. So these red dashed lines are X-rays coming from the source, and diverging X-ray lines. And along each of these red lines, the isodose chart is moved by a fraction of the air gap. So here's the air gap. For example, here is on the left-hand side, there is this air gap between the skin. The skin is a solid line that is shown with an S. And there's an air gap between the flat line and the skin, and this is called the H. And that at every dose point along the idealized dose isodose curve is now shifted down or up, depending on the flat line or below the flat line. So on the left-hand side is here you are shifting it down. On the right-hand side you're shifting it up by some kind of scaled amount of the air gap. And the scaled amount of the air gap is, there are some rules of thumb how you scale this. So this F times H. H is the air gap and F is the scaling factor. And the scaling factor is about 2/3 for cobalt radiation and about 1/2 for 18 MV X-rays. And notice that this H is varying along the skin surface. So the H, the air gap, is appreciable to as you go farther from the central axis, as is shown here, and is bigger as you as farther as smaller as you. So this is an approximation of an approximation. So this is even less accurate than the others. So just like for skin slope and patient geometric correction, there is an inhomogeneity correction, and also applicable to the traditional way of doing the dosimetry and dose calculations. So because patient tissue differs from water, like what we measured in the water tank, by also composition and also in density, this will alter the dose distribution. So we normally encounter 4 major inhomogeneities. One is the air cavities, like an intestinal lumen, lung, fat, and bone. And it will be very important to know the size, the shape, and position, and know their electron density and atomic number. So the manual correction methods resemble the skin surface correction methods. So here is a ratio of tissue air ratio method. So now we take the tissue air ratio or the TPR ratio. So T represents either the tissue air ratio or the TPR ratio, and then we form the ratio of that. So one of them in the numerator, this is evaluated at somewhat we call an effective or equivalent water thickness along the same ray, and then evaluated at the field size at that depth, and we form this ratio. So one of the TAR or TPR is evaluated at an effective depth, and then the other one in the denominator is evaluated at the actual depth where we define it. This effective depth is essentially a summation of the thickness of different tissues along the ray, as the photon ray goes through the heterogeneities, times the density of the tissue. So this is the thickness of the tissue times the density of the tissue of different tissue types as the photon ray passes through the heterogeneity. So this becomes what we call an effective or an equivalent water thickness along the ray, and that's what we are using in the numerator in the tissue air ratio or in the TPR ratio. So it's important thing to realize the limitations of this, because this corrects only the primary radiation. Sometimes we call it uncollided radiation. Primary radiation that comes from the source has not yet interacted, so it doesn't take into account the scattering. Also, it accounts for the field size and depth of the calculation, but doesn't account for the position of the point of the calculations with respect to the heterogeneity. So it doesn't take into account the shape and size of the inhomogeneity, and it has also assumptions as soon as it extends the full width of the beam and has a constant thickness. So this is not very good, but at least something. There is a better one, which is known as the power law tissue air ratio, the power law method, also named as Bezo, after the person who first introduced and proposed this. And this is, look at the cartoon to the left-hand side. So this shows a skin surface with incident beam, and then there is an inhomogeneity inside the patient. And we want to calculate the dose at some point beyond this inhomogeneity. So this is where the P is the dose point, AD is the beam size, the field size, really at this dose point, and we define two distances from the dose point. One is the distance to the nearest border of the inhomogeneity to the dose point, which is L1, and another distance is to the farthest point along the incident beam from the dose point. So this is L1 and L2. And then we evaluate the TAR, the tissue air ratio, at L2 with the given field size, and we raise it to the power of the difference between the densities of the two materials rho 2 is the density of the inhomogeneity, and rho 1 is the density of normal tissue. And then we divide this by the TAR evaluated at L1 with the same field size, except now this is to the power of 1 minus rho 1, which is again rho is the actual density. So this is a correction for the difference between water, whose rho would be 1, and the actual tissue density. So now this is much better because it accounts for the position of the inhomogeneity, but it still doesn't account for the size and the shape. And it also has a shortcoming that right at the interface, as we transition from the surrounding medium to the inhomogeneity, it predicts a discontinuity. And this doesn't happen. The dose is continuous. across. There may be some precipitous change in the dose, but the dose is connected to the boundaries. So this doesn't perform well right at the boundary. And it also exaggerates the correction for a point lying in the low density inhomogeneity. So if this were a very low density inhomogeneity, inside the inhomogeneity, this would exaggerate. So in other words, it neglects the backscatter from the underlying material. And also it's inaccurate when the lateral size of the inhomogeneity is small compared to the field size. If we, instead of the TAR, instead of the tissue area ratio, if we use the tissue maximum ratio, or the TPR, then actually it performs somewhat better. Now, what happens if the dose point is not outside of the inhomogeneity, but it's somewhere inside? So in that case, what we are using is the formula here, which is somewhat different. We are evaluating again the ratio, the tissue maximum ratio, whichever we want to use, the same way, except the exponents will change, rho 1 minus 1 in the numerator and rho 1 minus rho 2 in the denominator, and we scale this by the ratio of mu E and the mass energy absorption factors in the two media, in medium 2 and medium 1. So there is the equivalent tissue area ratio, which is yet another improvement. And eventually, once we go through here, I show a table where we compare all these correction methods. So the equivalent tissue area ratio, the ETAR method, takes again the TAR and evaluates the effective depth, which, as we defined earlier, at some kind of scaled field size divided by the tissue area ratio at the actual depth, wherever we are doing the dose computation, with the actual field size. And the question is, of course, how do we define the scaled field size? So this scaled field size is none other than the actual field size times a density correction factor. And the density correction factor is here. So it's kind of an effective density, because the way we calculate is that we look at the voxel in the medium, and it's a three-dimensional medium, of course. So now we have a voxel ijk position, and we look at this in a series of CT images, and we apply a weight factor. So we sum this times a weight factor divided by the weight factor. And the weight factor describes the relative contribution of each voxel to the effective density at the calculation point. And this weight factor is different at each calculation point. So this is much better. And here is a comparison. So I took it from Jim Purdy's publication. And so this is a comparison for 4 phantoms. So you see 4 phantoms, phantom 1, 2, 3, and 4. And phantom 1 is, they are all slab phantoms, but they have different compositions. Polystyrene, cork, polystyrene, phantom, etc. And as you can read here, and then the 3 and 4 also have aluminum. So phantom 1 and 2 are low density phantoms, whereas phantom 3 and 4 has high density inserts like aluminum. So these are the heterogeneities. Cork is heterogeneity here, and aluminum and cork are heterogeneities. So the TAR ratio is, as you see, it's not really performing well. So it's about 6% deviation plus minus 2.96. So this is percentage deviations from measurements. So the way that this was calculated is the calculation minus measurement divided by measurement. So this is a percentage deviation from the measurement. So about 6% plus minus 2% uncertainty. And for phantom 2 is 9%. For phantom 3, it's much better, but the uncertainty is pretty high, and the same way in phantom 4. Now, Bethe, which is the power law, is much better. So it's about 0.2% negative, but when we have high density inserts, it starts to break down 3%. It's not that bad. It's not, especially considering the uncertainties. The ETAR, the effective TAR, is looking much better, except for Phantom 4, but it is reasonable. And then the convolution and superposition methods, which we are going to talk about in a little bit, are of course much better. Still, the convolution is not as good in Phantom 3. So let's look at how the modern TPS, modern computer-based, and well, they're all computer-based. Even the old ones were computer-based, but these are high-power computer-based. Those determination methods are used. So here's a superposition principle. So what we do is that we have a three-dimensional distribution of sites where radiation interacts with the medium, and those at a dose point here, P on the left-hand side to see, can be considered as a sum of contributions of energy deposited from a small volume surrounded by P, but particles around this region P from infinitesimal small volumes of volume 1, 2, 3 around it. So particles that originate from these volumes will contribute to the dose in the region around P. So the primary photons will interact with these voxels all around the dose point, and every voxel will have its own little contribution to the dose point where we are interested in the dose. So let's move on. So here is a cartoon how this goes. So here comes the wavy left-hand side is an incident photon interacting with some kind of voxel here, and at P prime. And then based on this interaction, secondary electrons are produced, or maybe secondary photons are produced, or maybe this photon will scatter, and it goes in a different direction, and it will contribute to a dose point somewhere else. So we can formalize this, and we can compute this, and we can separate, we can subdivide the medium into an awfully high number of these small voxels, and we can compute the contribution of each voxel to this dose point. So the dose becomes an integral, really, over all these volume elements. So I take the integral, and of course this also depends on the energy of the incident particles. So it's also different energy particles every particle that comes in can have a different energy. So I also have to integrate the overall energies. So what I'm doing is using and this is a kind of a simplified way, the way that I wrote it, because it's using what we call the terma here. So this mu over rho is just the attenuation, the mass attenuation coefficient, times phi sub e. Phi sub e is the energy fluence. So this is known as the terma, the total energy released in material, and this happens at R prime, so this is in P prime, and this is multiplied by the dose kernel. This is the energy deposition point kernel. Sometimes it's called the Green's function. And the Green's function tells you the energy contribution by a particle that was generated at R prime location, and then it travels to the location of R, which is my preferred dose point, and it tells you what is the fractional contribution of this particle's energy into this point. And I integrate this over all volumes where the incident happens, and for all energies that particles can come in. So this is, in essence, the point kernel convolution superposition method. So the question is that how do you obtain this? How do you obtain this point kernel? Sometimes this is known as the Green's function. Sometimes people can call it dose spread array or point spread function. It goes by many different names. So the question is, how do we obtain this? Because this is not an easy thing to obtain, and obviously you cannot really do it by hand. You cannot do this integration by hand because you want to do it for an extremely high number of points where particles can scatter. So not only particles can scatter all around with many points and then contribute to this point, but now we'll have to get the whole dose distribution of the patient. Now I also have to have different dose points. So I have one dose point and I will have a calculation like this, and then I will have a similar calculations in a next voxel that will also contribute to X, and another voxel that will contribute, etc. And then the next round will be that the dose point will be changed into somewhere else, and then repeat the calculations. So how do you obtain these point kernels? So the standard method is Monte Carlo nowadays, is Monte Carlo computation in a phantom made of small adjacent voxels. So what happens is that these are the primary photons in this cartoon. As you see, these wavy lines are the primary photons that will interact in this voxel and will generate charged particles. And these charged particles, in turn, will go somewhere else. They may have a tortuous path and eventually end up and contributing to those somewhere else. This charged particle contributes to here, this charge here, and this one here. And these are computed using Monte Carlo techniques. So, and then eventually this is repeated for different voxels in every voxel, because every voxel will have its own contribution to this voxel. So this voxel will contribute a certain amount of energy to this voxel, and the next voxel will contribute to the amount of energy to this voxel. And then you have to repeat these calculations for all voxels. And eventually, you have to change the voxel location where you want to calculate the dose, and then redo it. So because this is the point kernel is a fraction of deposited energy per incident particle per unit volume, it must be normalized. So if you sum up all these point kernels for the whole volume, for the entire medium, it should give you 1. You can also separate the primary component from the scattered component. The primary is with a superscript 0, and it's mu en over mu, and the scattered component is mu minus mu en over mu. So Monte Carlo simulation is another can of worms. So I don't have enough time to give all the details of Monte Carlo simulation, but essentially it's a stochastic simulation, and we are simulating each interaction and energy deposition event in space. And we are following each incident particle. So these are, and not only each incident particle as they undergo various types of interactions, but we also follow their secondaries. So what you see is there is a collection of many incident particles, and we follow each one of them and how each one of them will scatter and will give rise to a secondary. And this is one would be called a history. And we repeat many, many histories to eventually we tally the dose contribution to a region of interest, and then repeat these histories and compute the average of many histories, and that average is going to be a good approximation of what is the actual dose. But because this is stochastic, it will also depend on how many histories I'm going to simulate. And if I simulate too few histories, then there's going to be a big noise in there. So there's going to be a big uncertainty. So I have to simulate an adequate number of histories so that the average will not be loaded with unacceptably high uncertainty. And the uncertainty in patient calculations depends on whom you ask what is acceptable, but we normally try to have 1% uncertainty. Certainly below 5%, but preferably below 1% uncertainty. So let's now move into how we do 3D treatment planning. 3D plans take advantage of an increased number of beams that are shaped by beam's eye view planning and conform to target volume. We can irradiate the patient coming in from many different angles with modern machines. So long time ago there were two opposing fields, or maybe a four-field way with wedges and compensators to irradiate the target volume. But nowadays, with the advent of sophisticated machines, we can have many different beams that can be used to target the tumor. So 3D planning emphasizes volumetric image-based simulation. And that it's of course its tolls, because it puts an increased demand to specify the target volume and critical structures with much greater accuracy. Because with a very sharp tool, you can escalate the dose to a very small area, but you have to now define that small area or small volume very precisely. So we need to have also more precise tumor imaging, better patient setup, reproducibility, organ motion assessment. Here is the outline of a delivery process. It has many different steps. One is starting with the treatment position, immobilization, and then patient and then fabricate the immobilization devices, place the radio-opaque markers there, obtain the topograms, perform the volumetric CT, etc. As you can see here, and these are it's pretty detailed, and I will go through at least some of the most important steps in here. So one is the immobilization and the planning CT. So first of all, we have to have a proposed treatment position, which is often based on critical experience. And the immobile, and of course we can also do iterative positions, as I will go into it in a moment. So the immobilization device allows a fairly accurate reproduction of the dose distribution from fraction to fraction, the patient repositioning, of course, and accounting for internal organ movement between fractions. And it's very important because inadequate immobilization can lead to bad treatment field alignment between fractions and intrafraction patient and tumor movement. So a CT is used to acquire a volumetric image of the patient in the treatment position. So it's very important that you acquire the patient image in the treatment position. So in this way, a virtual patient model is created, which is then used by the simulation software that mimics the function of the conventional radiation therapy simulator. So radio-opaque markers are placed then on the skin and on the immobilization device. So these are distribution markers to assist any coordinate transformation. Because in 3D planning, there may be some coordinate transformations, as we are going to talk about it in a little bit. And then you may have to use contrast agents to delineate the target volume in the CT procedure. And then usually we use a tumor resolution of 2 to 8 millimeter per slice, obviously better 2 millimeters, and the number of slices, 50 to 200 slices. And the geometry and the electron density data are extracted from the Hansfield numbers, and then they are fed into the 3D plan. So it is the definition of the target volume. So I'm sure that you have seen some of this. So this is related to the positions of the target volumes, the critical structures, and an orientation of the beams that are used for the planning imaging studies. So it requires use of multiple coordinate systems. One is related to the patient, and another coordinate system is related to the imaging and the treatment machine. So the positions of the target volumes and critical structures are related to anatomical reference points in the coordinate system. And the position and the orientation of these of the machines are defined in the coordinate system related to these machines. So the reference points that serve as a link or actually volumes. So we define these various volumes, as you can see here. GTV, which is in the center of this, or relatively in the core of this, is the gross tumor volume, which is the known tumor. CTV is the clinical target volume, and it includes suspected tumor infiltration into surrounding tissue. PTV, and I'm going to talk about ITV in a moment, PTV is a planning target volume, which has enough margin to account for set-off variations in organ and patient motion. ITV is somewhere in between, which is called the internal target volume, and this is due to the movements of the CTV reference to the patient coordinate system by internal and external reference points. And then there are a lot of IM uncertainties due to physiological variations, and that's physiological variations are difficult to control, but the setup is not as difficult to control. The setup margin is related to technical factors that can, like accurate setup and immobilization way. So these are the important metrics and definitions of the target volumes that we use in treatment planning. So the volume and the target volume and critical structure delineation is in modern treatment planning is loaded with the highest uncertainty of how the medical doctor will delineate the target volume and critical structures. And this is based on volumetric CT data. And the contours are drawn and displayed on the CT, slice by slice. And some of the organs at risk that have distinct boundaries, like skin and lung, can be contoured automatically. But others can be manually done by the oncologist. And this is where the uncertainty is. So with image segmentation, the contours are used to generate the realistic solid shaded surfaces here. And what you can see here on the left-hand side is a segmented region rendered in different colors. And this happens to be displayed by the beam's eye view. I'll talk about it in a moment, or in other planes. And on the right-hand side is a delineation by several radiation oncologists. So this is what I was referring to, the uncertainty. So depending on whom you are asking, which radiation oncologist, depending on their training, their history of the training, and their clinical experience, they can have different delineations, and some of these delineations could be substantially different. Look at the white line here versus the green line here. And this happens to show actually that if we have PET imaging, how this. So beam arrangement can have different aspects. So the treatment planning system can simulate the machine motion functions, and these are the gantry angle, the collimator, the length, width, and angle, the multi-leaf collimator, leaf settings, couch position, the lateral longitude, height, and angle. And this allows us to have the ability to orient the beams in 3 dimensions and then execute a plan or prepare a plan that use non-coplanar beams. Now, non-coplanar beams are the beams that are not in the same plane. It's a great way to do the treatment, but you have to be very careful to avoid the selection of a combination of gantry and couch angles that can lead to physical collisions of the couch and the gantry. And several accidents happen, even horrible accidents that affected the patient himself. So the essential features are the beam's eye view display. So on the left-hand side, you see a beam's eye view display, and an REV, which is a room eye view display, and the digital reconstructed radiograph, and the digital composite radiograph. And I'm going to through each one of these. So beam's eye view is an observer's viewpoint, which is at the source of radiation, looking down along the axis of the beam. and this is analogous to the simulator of radiograph or a port film. This allows us to easily view critical structures and volumes, and the shielding blocks and or the multi-leaf collimators. I can draw. For example, here is center. Here's a lung in which multi-leaf collimators are shown, and sometimes you see the patient orientation, like here in the lower left corner. The room's eye view is like an arbitrary viewing location within the treatment room. So this complements the beam's eye view in the positioning of the isocenter depth, or in visualizing all or any particular beam to see the beam arrangement geometry. So this is important because it allows you to draw the isodose surfaces or clouds in 3 dimensions. That allows you to evaluate whether or not there are hot spots or cold spots in the dose distribution, that you're underdosing or overdosing some volumes, or if you have an adequate coverage of the volume, sparing critical structures. So in the left-hand side, you see this room's eye view of different beam. On the right-hand side, you see the isodose surface or isodose clouds, and this is a prostate case that you can see there. The digitally reconstructed radiographs is something like it's to tie the old way of doing things to the new way of doing things, because it provides a planar reference as you use it to transfer 3D treatment planning to clinical setting. So it helps the verification of treatment delivery by comparing port films or electron or EPID images, and also allows the target volume and critical structure contours to be shown nicely. So on the left-hand side, you see a DRR, a reconstructed radiogram of a mediastinal field. Right side is orthogonal DRRs of a prostate patient. And many of these treatment planning computer software show additional information. Here, right below this, it shows the gantry and treatment couch position, and on the lower right corner, it gives you the patient orientation. So finally, everything can be actually put together in what we call a digitally composite radiograph. And it allows the CT numbers, different ranges of CT numbers that are tied to different tissue types, to be selectively suppressed or enhanced in the image. So now you have a great deal of latitude in visualizing certain structures. And it's very useful when you design the treatment portals. It gives you a better visualization of the organs, and portions of overlying organs of interest moved entirely from the image to further enhance the organ delineation. So what you do, in fact, some of the details is that the CT numbers are, as you know, the CT numbers, the Hansfeld numbers, they relate to actual cross-sections, interaction cross-sections, or linear attenuation coefficients, and it's relative to air. I'm sorry, relative to water. CT numbers are grouped into ranges corresponding to important tissue types, bone, fat, and muscle, and are modified by a weighting factor and then redisplayed. And this will give you an enhancement of tissue range, specified tissue range, compared with normal DRR. So this is what you can see here. So then you go into the dose calculation. So once you have the CT Hansfeld numbers, once you get electron densities for the tissue types, modern TPS, modern systems use Monte Carlo based or superposition convolution based, or nowadays even similar algorithms. There are some similar algorithms nowadays, modern ways. There's a company called Research, which is doing hybrid deterministic and Monte Carlo based simulations. the traditional methods are nowadays less and less frequently used. So, and this becomes an iterative process to find the optimal treatment parameters, because as you saw, you can approach and you can irradiate the target volume from different angles, from different beams, and both the angle, position, and the number of beams can be changed so that you can have an optimized treatment. And so this is an iterative process, and you want to find a best arrangement, and then during the iterative process, the arrangement is modified based on the dose distribution that you see as you superimpose on the CT images. So this means that you also generate a huge amount of dosimetric data, and it becomes increasingly difficult to, first of all, display and then analyze it. So as you see in the front of the computer screen, you go through all these slices and maybe you spin around in a 3D fashion, and it becomes very difficult to analyze what you actually are seeing and how clinically this could be related to clinical outcome. So this requires some kind of data reduction, which we're going to talk about it in a little bit. Now, because this is an iterative process of how to find the best combination of beams and even energies nowadays, is the best way of doing it is some kind of inverse planning. In the inverse planning, you automate this iterative process, and you design the most appropriate fluence profile for each beam so that you optimize the dose distribution. So what you do is just do the other way around. So instead of first calculating the dose distribution and seeing whether that is good for this patient, what you want to do is you outline the dose distribution about the different targets, and then you calculate backwards that what is the optimal beam arrangement in order to meet my requirement to this particular dose distribution. So this, of course, requires that the dose computation be repeated for many beams, many times, and many points. So this is extremely computationally intensive process. So those volume histograms. So this allows you to tie it more into clinical outcome. It displays the normalized percentage of volume of interest exposed to a defined dose. So we distinguish two kinds of DVH. One is a differential DVH, and the other one is a cumulative DVH. And the differential is based on simply subdividing the volume of interest into a grid of voxels. So on here on the left-hand side is the patient, and then just a cartoon of irradiating a volume of interest. And in the center here, we subdivide the volume into voxels, small voxels, bins. We can call it dose bins, and the dose distribution that you calculate here within these voxels is then divided into the bins, and voxels grouped according to the dose bin, without actually regard to any anatomic location. So then you plot the number of voxels, or the frequency distribution, which is the number of voxels, which is on the right-hand side, on the vertical axis, in each bin versus the bin dose. So this is the dose in the bin. So this is like a frequency distribution, and this is known as the differential DVH. Now, most of the time, what we use is the cumulative DVH, and the cumulative DVH is a plot in which each bin represents a volume, a percentage of volume that receives a dose equal to or greater than the dose indicated on the x-axis. So this is the way that we do it. So this is, on the left-hand side is the differential, and on the right-hand side is the cumulative DVH. And the value at any dose bin is computed by summing the number of voxels corresponding to differential DVH to the right of that dose bin, right? So this is, you're actually summing this to get the cumulative DVH. So the volume value of the first bin is the full volume of the structure, because the volume, that is the volume that receives the least zero dose. So the volume for the last bin is the one that receives the maximum dose bin. So this is summing the frequencies. And then you can do this for various organs, various targets. So here on the right-hand side, you see that, for example, in this example, these are cumulative dose volume histograms for the eye, for various other structures, and this is the CTV, the GTV, etc., as we discussed. So the utility, what is the utility really of this DVH? And so the DVH for various types of targets, like the planned treatment volume or the organs at risk, can be superimposed, and you can compare them from several competing plans. So it would be plan A better or plan B better, and this way you can find regions that are overdosed, as well as any other target volumes that may be underdosed. It does not provide any spatial information, however, so you cannot really use the DVH alone, not replace the spatial dose distribution displays. So I guess this is because this is a finite time, you know, to give an overview of treatment planning. I guess this is the end of it, and let me know if you have any questions. So thank you very much for your attention.
Yeah, thank you very much, sir. So question time, please. Say look. Hello, question time. You can type your question also.
Yes.
Okay, this is from Adeniji, and she's asking, what is a scout film?
What is a scout beam?
Beam.
A scout beam, well, is it in terms of, I'm sorry?
Yes, you're correct. A scout beam. I think that's what you mean.
Scout beam. Yes, this is usually the CT planning phase, but depending on where on what context, because it can have many contexts. In the context of CT planning, the scout beam gives you the outline of the patient. It doesn't give you the detailed 3D distribution of anatomical information. It gives you pretty much a patient location and a very rough overview of patient. Even some heterogeneities might be distinguished there. So that's why we call it a scout beam. So we are just looking at generic information about the patient size, maybe some heterogeneities, but not as a very detailed information on a voxel by slice by slice, voxel by voxel basis.
Great, thank you. So, any more questions, please? Okay. So, does anyone have any more questions? Beam. But is there any such thing as a scout field, not just beam?
I'm sorry again, please?
Is there any such thing as a scout field?
Scout field. Well, yes, it's actually it's a field, you know, in the CT, again, in the CT context. This is not, sometimes it's not even the same beam which is used for the actual CT scanning. Sometimes it may be an isotope, like a cesium isotope, that is used, a low activity cesium isotope, which provides a field essentially. So it's a radiation field. But you can also use the actual X-ray tube. In some cases, you can use the X-ray tube, and it generates a field. So whenever it's from the perspective of radiation transport, you know, you have to think in terms of a beam generates a field. So a beam is not necessarily a pencil beam. Nowadays, you can think about a pencil beam in case of IMRT. intensity modulated radiators, multi-leaf collimators, right? So you can have the collimators set up so that you're going to have a very thin, narrow pencil beam. But most of the time, the beam is a volumetric beam, and it gives you a field. So even a scout field can be envisioned this way, that you have a source of radiation which will generate a field. So the field, you imagine that it's not just in a beam of radiation, particles, not all particles will move in the same way from coming out from the source, and then they will go always away from the source. Particles are going back and forth, especially once they hit the patient or the patient's skin. There's backscatter, there is side scatter, there is all kinds of particles that go in all kinds of directions. So that will generate really a field that even now at the source of the radiation, you can, if you had the detector who could detect it, even at the source of the radiation, you're going to see particles that are coming back from the target. So that generates what we call a field, a radiation field. So, and that eventually will tie into the concept, or we call it a phase space. A phase space is the voxel by voxel or spatial point by spatial point variation of the radiation field.
All right.
Was a question there, or?
Yeah, that's clear. So thank you very much. Dr. Olajide Babidele, do you have a question? Because you were speaking. Hello. You can type your question if you have any, in case you are not, the audio is not good.
Well, unfortunately, we cannot hear very well. But you know what we could do is then write these. We can write these questions or email these questions. I will be happy to answer to any email that I receive.
Okay, thank you. So I have another one from Dr. Akintayo. He says, is the irregular field algorithm Clarkson integration from a precise plan 2.16 still modern?
Oh, very long. Can you say it again, please?
Is the irregular field algorithm, I think, called Clarkson integration
Is
from a precise
collapsing integration?
Yes, from a precise plan still modern? That's from a precise plan 2.16 still modern? That's what he's asking. I don't understand the question very well.
I don't understand the question.
Okay.
Is this still modern, meaning that this is up to date?
Yes.
So irregular field, if I understand it correctly, we are looking at an irregular field,
Yes.
which is irregular irradiation field of the tumor, and we collapse it and integrate it.
Yes. I don't get that. So the Clarkson integration? Okay. Maybe I'll allow Akitayo, please, you can speak up if you have a microphone. I don't know if you're hearing me clearly. But someone else asked a question now, Dr. Emmanuel, say, what treatment planning goal in terms of DVH should be aimed at based on different tumor sites?
Well, yes, I think this is a question for radiation oncologists or different tumor sites. What would be the best DVH for different? Well, it's for different tumor sites and different tumor types. DVHs will be different, but you know, I'm not qualified to tell what is the accepted DVH for different tumors. So this is more like a question to a radiation oncologist.
Okay, thank you. So, hello.
Hello.
Yes, please, you can speak up. We can hear you.
My question is concerning the irregular field algorithm.
Yes.
Irregular field algorithm. Okay.
Yes, in one of the centers where I actually did a bit of some work, it's actually an Electa product. So it's based on area integration algorithm, which is from previously published method, Clarkson integration. So it uses irregular field algorithm, sort of. So I'm trying to describe the treatment planning system It's a 2.16 treatment planning system. So my question is, I don't know whether it is still. So I don't know whether this treatment planning system is still modern or it is a bit outdated. I want to get some information about it and what are the implications.
I'm not familiar with this. I'm not familiar with this particular treatment planning system, but you know the irregular field. So that's very important because we do, like for example, 4-field or 2-field opposing field. You're never going to get irregular fields. So just by virtue of having an irregular field, it means to me that there is either an IMRT there, or maybe a TOMO, or maybe some other ways that you can deliver radiation from various different angles, including non-coplanar. So if this refers to non-coplanar delivery, then a lot of centers, even in the United States, are still using this.
Okay. Okay, that's fine.
Yeah. All right. Thank you very much. Do we have more questions, please? Okay. All right. Thank you very much. In the absence of any more questions, I think we'll take time to digest the class. Dr. Sajo, please, I'll forward them the class notes. Someone just asked me for the class notes.
Sure, please. The whole how do I do? It's a huge file. The PDF. I can make a PDF, or I can upload it somewhere, and then you can download it from the cloud.
Okay, yeah, I think you can do that on Google Drive. Is that possible?
I can do it in Google Drive. Yes.
Yeah, you can. So you can use my email. I'll send it to the class and send it to them by.
Very good. I will put it up in the cloud, Google Drive, or my institution's own drive.
Okay, no problem.
And I will provide a download link to it. Do you want the whole the PowerPoint presentation or a PDF version of that?
We can get the whole paper presentation and the PDF version of it as well. Yeah, anyone is fine.
Okay, anyone is fine. The thing is that because this is huge, and if I make a PDF out of it, it will not as big. But I can post it. So sure, I will post it and then send you a download link, which you can then distribute among the audience.
Okay. Yeah, nice. Thank you very much. So I don't know, maybe in subsequent class you could have time maybe to teach us the artificial intelligence components of treatment planning. Because I have people who I sent an email. Just someone is asking me here, but I sent an email telling us that we'll be dealing with the treatment planning system for this class. Someone is
right. So intelligence is yet another. Yes. So this is in a finite time. I wanted to give you an overview of treatment planning.
Yes.
Artificial intelligence, and there are some other things. Inverse planning also would require more time. Yeah. So we can schedule another one based on artificial intelligence.
Okay.
But we can talk about it sometime later.
All right, no problem. Thank you very much.
I can tell you this is artificial intelligence is very much up forefront, and nobody has implemented artificial intelligence really in treatment planning, and people are just thinking and talking about it, but sometimes we don't even know what is important and what's not important.
Wow.
So, yes.
Wow.
So artificial intelligence is something of a great promise, but you have to wait until it all boils down of how we do this, because you need to gather enough data and then teach first of all write computer algorithms, teach them, and there is no consensus what is the best way of doing it. People are people are proposing things, but currently I don't think that there is one way that there is a consensus based on well, this is the way to do it. So I think we just have to wait and see, and some of us actually may be active in that and do research on that.
Yes. Great. We'll like that very well. So yeah, we'll talk about that later, and then I'll inform the class of any update on that for now. But please, I actually send a notice for that person who is asking that today's class will be strictly on treatment planning. Maybe you missed the email or something. That's talking to Dr. Maruf. All right. Thank you very much, everyone, for today's class. I'll forward the notes. And thank you very much, Dr. Sajo, for taking your time.
Thank you.
Yeah, thank you.
Thank you very much for listening. Thank you very much for your attention.
Yeah.
Thank you, and have a good day.
Yeah. Bye.
Bye-bye.
Bye.